Hello, good afternoon. Can you hear me?
Yes, Prof, we can hear you.
All right, thank you very much. Okay, today our lecture will be continued on the chapter 2B, okay, which is correlation theory and analysis and some applications. After we already looked at the impulse and time response identification plus frequency response identification last week. Okay, so the second one is the correlation theory, analysis, and applications, which mainly will discuss on the two types of correlation functions known as autocorrelation function or ACF or cross correlation function CCF. Okay, so what is ACF and CCF? So ACF is a graph of correlation coefficients relating two versions of the same signal. Okay, so if you have random signals from one source, then we duplicate that random signals and then we autocorrelate each other, meaning that we are doing trying to correlate between two versions of same signals. Okay, that is the keywords plotted against shift in time. While the second one, which is a cross correlation function, is the graph of correlations coefficients relating two different signals plotted against the amount of time shift between them. Okay, so that is the basic difference between the ACF and CCF. I can see that ACF describe particular signals, while CCF describe the relationship between two signals, two different signals. Okay. Right. In correlation functions, we always have non-deterministic signals which cannot be defined by means, okay, of an explicit functions of time, but must be instead be described in some probabilistic manner. Okay, so when we undertaking system ID experiment with non-deterministic forcing function and carrying out the analysis in the time domain, the appropriate statistical descriptions for the signals are termed as correlation function. Okay, so mathematically, the correlations of two random variables is the expected value of their products. What is the similarity between two different signals? What does it inform us? Okay, it shows whether one variables depend in any way on the other. Okay, between these two different signals. So if the variables have a non-zero means, okay, it is sometimes preferred to subtract the mean value before determining the correlations. Some signals have a DC offset, so we have to move the DC offsets in pre-processing system ID procedure. And this will help, okay, to find another terms that we call it as a covariance. Okay, so if the two variables are values of a random signals, okay, for correlation function at two different time instances, then the expected value of the product depends on how rapidly the signal change. So we have a high correlations, we have a low correlations. So high correlations meaning when two times instance are very close together, okay, but much less correlation when the time instant are widely separated. So that is the keyword for high correlations and low correlations, okay, or less, we call it as low. So thus, it is important it is appropriate to define correlation functions or covariance functions. Sometimes people say as covariant functions after you move the DC sets, in which the independent variable is the time of separation between two random variables. If the random variables come from the same functions, we call it autocorrelation. If the random variables come from two different functions, so we call it as a cross correlations. So in autocorrelation, in ACF, it established the relationship between the signals and the time-shifted version of itself. So this is this relations is possible for all time shift, okay, and described by ACF. The value of the autocorrelation function for a delay time t is called autocorrelation coefficients. Okay, so it's like a graph, okay, like this. This one we call it as a x bracket t, x signal. The second x is the duplicate of that previous signal. Okay, so we can calculate autocorrelations either using a software or using a hardware. So if you have more money, big money, so more budget, so we can go for instruments. Okay, any instruments provided by Hewlett-Packard, provided by Feedback, and so on, which is known as the autocorrelator or correlator. So the schematic diagram of the autocorrelator is shown here, where this is the random signals, and we have a sampling circuit. Okay, and this sampling circuit will go to the shift register, right? Okay, first time delay, second time delay, third time delay, fourth, and so on. And we have a switch over here. Okay, and then we'll multiply, and then we average, then when we plot and display the value of the correlation coefficients versus time delay. Okay, so this is the equipment, okay, for the cross correlator hardware. This one is from National Instruments. Okay, so most industrial academy in the laboratory have this kind of correlator. Or if we don't have any budget for that, so we can simply choose a software that can calculate and display like this. Okay, so this one can consider as a low cost, and this one high cost. Okay. So the autocorrelation function in terms of mathematics is shown here. Phi xx tau, tau is the time delay, x and x is the same signals. Okay, limit t to infinity 1 over 2t xt plus tau dt. Okay, so this is known as autocorrelation functions, mathematical descriptions, and also it can be written as this one, xt minus tau xt. So we have some sort like positive and negative. This one is towards negative, this one is towards positive. Okay, and this is the functions. So autocorrelation function or psi phi xx tau is the time average of the product of the value of the function t second apart, okay, which vary from 0 to a large value, and averaging being carried out over a long period of 2t. Okay, so this process is graphically in the next figure. Okay, so I can show you this one. Right, we have one signals which is xt, and the second signal is xt plus tau. So the same signal shifted by tau 1, tau 2, tau 3, and so on. Okay, and then we will be multiply each other. This one will multiply each other. Okay, and then being average. Okay, and that value is plotted here. Okay, it's plotted here. So this is the ACF versus time delay, and this one is a random signals, and the second one which has shifted by tau. So from the figure, it consists of operation of displacement, okay, shift or displacement, xt through a time t, multiplication by xt plus tau. Okay, this one multiplied and being averaged, okay, to give the value of autocorrelation functions for a single value of tau. And this is repeated again until to the large value of tau. Okay, so it is a measure of predictability of the signals at some future time based on the knowledge of the present value of the signals. So that is the concept of ACF. So if the value tau seconds from now is closely dependent on the present value, then psi xx tau will generally be large. Okay. For example, we have a rectangular pulse, okay, and then a second one will be shifted, okay, by tau, okay, something like this, okay, and then will be multiplied, and then will be averaged for some looping until a large value, and then plotting. You can see that tau equal to cos 0 will give a maximum value of autocorrelation functions. Okay, so this one is by xx tau. For example, we have a sample of square wave. Okay, so we take 20 samples. This is 5, 5, 5, 5. So we have 20 samples. Okay, and then we plot it here, right, as a wave. And this one is the duplications of the W. And then this is a product. Okay. Then at time delay equal to 0. Okay. So we just multiply. And then we get this one. And then we total up and average, total 20, average 20 divided by 20. And this is the first autocorrelation coefficients. Okay. Then for time delay equal to 1, so the signals has been shifted. Okay, each of them. Okay, shifted. Previously is this one. Previously is this one. And after tau equal to 1, so it has been shifted to the right, and -1 replaced because this is the, what do you call that, periodic signals. Then continue multiplications. Okay, and this is the product. Average 16 divided by 20, the second value of ACF. Okay, so we continue shifted at time delay 2. Okay, shifted again, time delay 2. W no shifted, only D. Okay, we shifted. Then find the total is 12, 0.6, and so continue for tau equal to 3, 4, 5, 6, 7, 8, 9, and 10. Okay, and then we get all the value of the autocorrelations. Then we plot it. Okay, so you can get something like this. Okay, is a triangular wave. Okay, is a triangular. Okay, this is the autocorrelation functions, which is x tau, and this is the tau. Okay. Well, simply this is the to understand the concept. So we show some shifting using tables, but you can do it by computer program. This is computer program that I designed. Okay, for the process to achieve autocorrelation functions. Okay. Let's say we have a random noise here, the data, okay, and then we insert inside this program, okay, the data itself, which is the W, and then duplicate by tau, okay, and then we can get something like this, which is tau equal to 0, give the ACF maximum, okay, maximum value. Let's say a simple program, y is equal to random 1 to 100. Choose any number between 1 to 100. plot, okay, and then y transpose, okay, transpose, this one meaning transpose, interchange between row and column, okay, and y dot, y prime, and then apply the kx score for u and y, okay. Then the random signal, this is the random signals that we generate between 1 to 100. And the autocorrelation function is shown here, where tau equal to 0 give a maximum value of 0.36. Let's say we change from random signal to sine wave, okay? Phi multiplied by sine x, so find the u, find the y, then kx score u and y. So we get a sine wave over here, then the autocorrelations is the shown here, okay, which is a sine to cosine, okay. It looks like cosine, but it's not cosine, okay, have a value. So for example, consider the deterministic signals, which is given here, okay, f1 a sine omega t plus sine, a sine wave with the amplitude of a, frequency of omega, and phase of psi relative to 0, time data, shown in the next figure, which is here, okay. So we applied autocorrelation functions, which is here. So the maximum is a squared divided by 2, and it will repeat again. But here, because these signals is what do you call that as periodic signals. Okay. So the SAF also will repeat accordingly to the periodic signals. So what we do is we apply the mathematics equations here, a sine omega t plus psi, okay, so multiply by a sine omega t omega tau plus psi. So this is the time delay factor, okay, time delay factor. So since the signal is periodic, so it is theoretically only necessary to average over one period of time 2 pi over omega, where omega is the frequency in radian per second. Then we apply the calculations, okay, integrations, and to simplify this, okay, so let u is equal to omega t plus psi. So therefore, we apply differentials, okay, du and dt, since psi is a constant time delay, and the work is shown here, okay. U sine omega t plus psi, so simplified. So this is almost a mathematics, and at the end of the day, we get a square plus cos omega tau, yes. Okay, so if the signal is sine wave, we apply autocorrelation function, so we get a cos, okay. It's proven here, cos omega tau, by mathematically derivations. Cosines, okay, this is a cosine. Apply autocorrelation functions, okay. So the cosine will give ACF of cosine wave as well, okay. So it's not a sine wave, but it's a cosine wave. So we can prove it by this one, okay. But I leave it to you, okay. Leave it to students to derive, okay. For derivations. Okay, you follow like the previous examples. The answer is in cosine, okay, it's a cosine wave. So also we applied for random binary signals, okay, which is one of the important input signals, okay, for system ID, okay, which is shown in the 3.5. So this is the random binary signals, okay. Delta t is the sampling time. So I will discuss this later in the next chapter, chapter 2C. Okay. So the autocorrelation function is triangular, which is maximum at tau equal to 0. Because it's the random nature of the random binary functions. The name also random. So that's why the autocorrelation is maximum at tau equal to 0. Okay. So this is a sample of PRBI signals. It can be generated using a software or using a hardware. Okay. And then can be applied autocorrelations. So since the signals is periodic, this is one period. So after one period, it will repeat again the same signals from here. But inside here is random. Okay, is random. But at one time it will be periodic, then repeat again, random. So you can see that the autocorrelations repeat after 15, according to the signals above. So the calculation is shown here. Okay, but will be deep in discussions in chapter 2C. Okay, so it's involve delta t, which is the sampling time, and the time delay. Okay. Another example is white noise. So white noise usually is a noise came from the several sources. One of the sources is from the lighting. Okay, light in the room. Okay, lighting in the room. So usually we can apply an autocorrelation function for these signals as well. So the definition of white noise is a random signals or processed with a flat power spectral density. So that is a white noise. And the signals contains equal power within a fixed bandwidth at any center frequency. So it draws the name from the white light, okay, in which the power spectral density of the light is distributed over the visible band in such a way that the eye's 3 light intensity receptors are approximately equally simulated. We can do some calculation on that, okay, for the white noise, okay, by assuming as the function of f3 square, which is a mean square value. And the autocorrelation of a white noise thus consists of an impulse of magnitude equal to the mean square value occurring at tau equal to 0, and the rest of the value is 0 elsewhere. So for autocorrelation functions, there's a properties, okay, that we must understand and we must know, okay, as shown here. So ACF is an even functions, okay, is an even functions of tau. So psi xx tau is equal to psi xx minus tau, okay, on the left and on the right, because the same set of product values is averaged regardless to the direction of the translational time. Even functions. And then psi xx 0, when the time delay is 0, is the mean square error value or average power of xt when tau equal to 0. Then when psi xx 0, which is tau equal to 0, is the largest value of the ACF, but if xt is periodic, then psi xx tau at any value except 0 will have the same maximum value when tau is an integer multiple of t period. Okay. And if xt has a DC components, okay, let's say 1 volt or 5 volt or mean value, then psi xx tau also has a DC component, the square of the mean value. That's why we have to move the DC component of the signals when we apply ACF. So if xt is a periodic component, the psi xx tau also has a component with the same period but with a distorted shape, resulting from the lack of discrimination between the phase, okay, of the original signals and the shifted time signals. So xt is a random component, so you can see that psi xx tau is towards 0, okay, as tau towards the infinity. So a given autocorrelation function may correspond many time function, but at one time, but any one time function has only one value of ACF. So we have about 7. Okay, just remember 3 or 2 is more than enough. Okay, for the properties of the autocorrelation functions. So if you understand ACF, so cross correlation function is not a big deal, because CCF is just comparing one signal with another by multiplication of the corresponding instantaneous value and taking the average, because it's two different signals. Okay, you have omega, which is the first signals, then D will be a second signal, not the same as omega. So CCF is the graph value of the coefficients versus parametric time shift, is a measure of similarity between two different signals. That is the keyword. Okay, so in this case, if you have an unknown model, and this is the input, and this is the output, so we captured here and find the psi xy. Okay, so that is the cross correlation between the input and the output. So frequently, there exists two signals xt and yt, which are not completely independent. Okay, so in system ID Si, this value will be an input and the output. Okay, is a measure of the dependence of one signal to the other, is given by the cross correlation functions. Okay, of course, when we inject the signals, okay, we want to see the response, definitely. Okay, so let's say we have a square wave as x, and y, we observe the output. Okay, so it's try to follow the input if the model is linear. Okay, if not, it's not linear or non-linear, so we have to figure out what is the non-linear factor in that mathematic in this model of the unknown model. So mathematically, we can describe as these functions. Okay, xt plus yt plus tau, okay, multiply, or simply yt, x will be shifted. For this example, x is not shifted, but y is shifted. But for this one, y is not shifted, x is shifted, but both are the same. Okay, you can define either the first one or the second one. So the cross correlation function relating two continuous signals, if the signals is measured in time domain. So r, x, y, tau, x is the first signal, y is the second signal, both are different in time domain tau. Okay, so limit t towards infinity is shown here. And then when you apply in the discrete form, digital signals for programming, so we just name it as xn data and yn data. Then we apply the equations, so we can get the cross correlation function either in continuous time or discrete time. Okay. So two analytical functions are defined. Okay, time shifting y and shifting x. If the two signals are from independent source, so they have a zero mean values, then the CCF will be zeros and the signals are said to be uncorrelated. That's why if we have a mean values of x average and y average, both are non-zeros, then the cross correlation function has a DC value, which is equal to the x multiplied by y average. So since CCF is not an even function, so this type, there is type of symmetry in this CCF functions, which is known as psi xy tau equal to psi yx minus tau. Okay, so this one towards the right and this one towards the left. So when you fold the graph at the y-axis, so it will be symmetry between each other. For CCF, when tau equal to 0 and psi yx equal to 0 have no particular significance, the CCF generally does not have a maximum at tau equal to 0. It's not like a cross correlation functions. Okay, so very rare that cross correlation function have a maximum at tau equal to 0. Okay, because it will give a maximum at some certain time shift. So the ACF of the sum of two signals set in sine wave plus noise can be expressed in terms of the ACF and CCF of the individual signals as shown here. Okay, so you have a psi x plus y tau, okay, applied into the mathematical equations of the CCF. Then you simplify, okay, the equations. So provided that xt and yt are uncorrelated, then the third and fourth term each have the value of x multiplied by y average, and it will give you these expressions where is equal to psi xx tau plus psi yy tau plus 2x average y average. So this is the ACF of x. This is the ACF of y. When you apply cross correlation functions plus the DC component. So in order to carry out cross correlation, we have a lot of methods: point-to-point method, polarity method, evolution method, skip algorithm method, zero crossing method, and frequency domain method. Let's say we have a sample of square and triangular wave is shown here, the data. Okay, and this is the time. Okay, between 0 to 19, almost 20 data. We have 20 data of x and y. So examples of CCF for rectangular and triangular wave is plot here. Okay, so this is x and this is y. So for time delay equal to 0, so this is your square wave just now, SV, and this is your triangular wave. Okay, so 1, 1, 1 minus 1. Okay, correct, and then this is triangular. Then at tau equal to 0, when time delay equal to 0, multiply each other, then average the total up and then average. So the total is minus 20 divided by 20 data, so minus 1. This is the first CCF function, CCF coefficients. Continue, shifted, this one, shifted, okay. In B, all are shifted. This one, maintained, no shifted. After shifted once at tau equal to 1, then multiply, then sum, total up, then average, minus 44 divided by 20, second cross correlation functions. And this one continue again for time delay equal to 2, shifted again, multiply, total up. So you get the minus 2.6 for the cross correlation coefficients. Continue for tau equal to 3, 4, 5, 6, 7, 8, 9, and 10. And finally, you plot it up. Okay, so you get something like this at tau equal to 0. Okay, this is the coefficient, the first coefficients. And the maximum coefficients occurred at tau equal to 7. Okay, so not tau equal to 0. Okay, because we are correlate between two different data. So if we have we generate a square wave, we generate a triangular wave, and we are using the programming that I given just now. So you can see that the cross correlations is about similar like the one that we do it manually. Okay. And in order to do that, we have algorithms, okay, a flow chart. So we start here. We collect the data. Then we assume L equal to 0. Okay, then we shift it. Okay, then we have a decision, yes or no. Then we sum up. Then we average. Okay, and then we end it here. After we store the cross correlation coefficients, or we modify it for faster calculations. Shown here, some of the functions are ignored and replaced by others. So this modified method is much better. Okay, which I use this one for the programming just now that I show in the listing. Here. Okay, so I use this modified and put in the KX score. Okay. The difference between this one and the previous one is we use U and Y. Okay, U is other signals, Y is second signals, the different signals. The concept still the same. Okay, and we have a hardware for cross correlator. Okay, the schematic is quite different from the autocorrelator, because we have two sources, which is the signal 1 and signal 2. Both are different. Goes to the comparator, goes to the shift register, then go to the multiplications, averaging, and then plotting the coefficients. Or if you don't want to be headache, so you just buy a staff by Agilent's 35670A FFT spectrum analyzer, which can give you the cross correlator, because we have two channels, channel 1 and channel 2. Okay, so we can do using by pressing the functions given in the equipment, so we can get cross correlations. Right, so some questions for you to ponder for question 34. Okay, so I just leave it there. Okay. So you can try and solve it. Question 35. Okay. You can get it from any resources. Okay. For exercise. So we stop here at slide 89. So during fasting time, I give a lecture for 1 hour. Okay. Since I cannot drink in the day, so I make an excuse that I just make for 1 hour class. I hope it's okay for you all. Okay, shall we continue in on Thursday, 11 a.m.? Is it okay?
Okay, bro.
Okay. So we ended here and see you on Thursday. Guys?
Okay, Prof.
Okay, Prof.
Okay, thank you very much. Assalamualaikum.
Thank you, Prof.
Thank you, Prof.